Hello everyone and welcome back to another little video where I dig further into polar coordinates, and this time around I talk about how to find the arc length of polar curves. Now if you watched my previous video on parametric equations and how to find the arc length of those, you might remember the result that I got there on how to do so. So the reason I can use this result here is because what are polar coordinates other than a parametrization of Cartesian coordinates in terms of theta? So this t basically becomes theta for us. Now, we know the relationships of x and y to r and theta, as we can see here. You might be wondering, why didn't you say that your parametrization is in terms of r as well? Because r, if you recall, is also a function of theta. So really the parameter here that you're parametrizing polar coordinates is literally the angle theta. So if we can get these derivatives that you see on the left here, we might be able to actually have a shot at finding the arc length formula for polars. Let's do exactly that. I'll start here with dx d theta, meaning I'll have to take the derivative with respect to theta of r cos theta. Both of these are functions of r, so this invites the use of a nice little product rule. I go over here then, first take the derivative of r with respect to theta, leaving cos theta untouched, and then I go ahead and add the derivative of cos theta, which is negative sine theta, and then r untouched. So I might put that r actually at the front here like this. Done and done. Then we can go and look at the derivative of y with respect to theta. And so we have to take the derivative of r sine theta with respect to theta. Again, another little product rule over here that we have to do. So first we take the derivative of r with respect to theta, leaving our sine theta untouched. And then we take the derivative of sine theta, which is nothing more than cos theta, and leave our r untouched, which again I'm going to prefer to put at the front like this. Okay, so these are the derivatives. The next move here that I want to do, obviously you saw that I need to add their squares, so I'm going to do exactly that right now. So I'll lay them out like this, and then I will have to do some really interesting unfoiling to get what I want. But it will work out. It's a little bit tedious. However, it is faster than deriving it from the plots like I did for the parametric equation version. Okay, so we have these laid out. We make sure they're written right, because if we make a mistake in here, it's going to be a mess to fix. And so we start. So we have dr d theta all squared cos squared theta from this term multiplying itself. Then we got 2 times these two terms multiplied together. That is 2r dr d theta sine theta cos theta. And then this guy here multiplied by himself gives us r squared sine squared theta. Okay. And then we go over here and start unfoiling. So we've got plus dr d theta all squared sine squared theta. And then the intermediate cross terms here give you a plus 2r dr d theta sine theta cos theta. And then the last term here, as you can see, gives us here a plus r squared cos squared theta when it multiplies by itself. So let's take a look. Immediately here I see a cross term canceling right here. So that big boy goes away. And we can see that I can do a little bit of factoring here because these carry the same derivative. So I can pull this derivative right now, factor it basically, and be left with cos squared theta plus sine squared theta. And then for the other remaining terms here and here, I can pull the r squared and be left with sine squared theta plus cos squared theta. Now, of course, the sums here of the square functions, the square trig functions, is 1 from the known identity that we have. And so you can see what the final result is. It's just the r itself squared plus the derivative with respect to theta also squared. And of course, that was in the end, we wanted to square root this quantity, right? So if we do so, if we put that square root all over our results here, we get this. And this indeed is our little ds right now. I haven't put the d theta in yet. I'm going to fill it in a second. So this is the inside bit of our equation that we're developing. Now when we put it all together, we're going to have for the arc length that it is the integral between two angles, theta 1 and theta 2, of the square root of r squared plus the derivative of r with respect to theta, all squared, and then d theta is sitting at the front. That's the parameter that we're integrating over. And that's it. That's our formula that we can use for arc length and polars. From here, I'm going to go ahead and apply it as usual in a couple of little examples here. We're going to try and find the arc length of the left and the right functions here. And let's see how it plays out. Typically, again, these arc length integrals can tend to be pretty nasty. But again, for the examples that we are including here, they're going to turn out, to be pretty okay. All right. Again, being familiar with trig functions here is a must as you're integrating through these equations. The first one over here, it's telling us that it's going from 0 to 2 pi. It's being kind enough to give us the interval. And the function itself, if you can see, is e to the theta over root 2. Again, that's what we're putting in here, so it's going to be getting squared. Now, as for the derivative right now of this function with respect to theta, right, it would be nothing other than really itself. It's literally itself. So I'm going to put in the position of this term, I'm going to put in e theta again over root 2, all squared. And then at the front, of course, sits the d theta. So as you can see here, as I'm moving along, I basically get the integral from 0 to 2 pi. And then when we distribute the square inside these terms, we essentially get e to the 2 theta by exponential rules, divided by square root of 2 squared, which is 2. And then we add here the same thing. Obviously here, these add to give you just e to the 2 theta. That's all that we get. It's 1/2 and 1/2 after all. And one thing I want to see here is, I want to notice that taking the square root of something is like raising it to the 1/2 power. So this 1/2, is going to multiply this 2 theta right now to leave you with just theta. That's what's going to happen essentially. You're going to be integrating, after all of this work, just e to the theta from 0 to 2 pi. And of course, the integral of e to the theta is itself. So we're going again from 0 to 2 pi. So our result here is e to the 2 pi minus e to the 0, which is nothing else other than 1. And that is our answer for the value of the arc length. Not too bad. So the next example over here that I've got lined up is a little more cumbersome. So again, we got to fill in this equation. That's what we're trying to do to calculate the arc length now. So r squared right now, let's just do it piece by piece. So r squared is going to be 1 minus cosine squared, or 1 minus 2 cos theta. Forgot the theta here. Pardon me for that. And then the last term is going to be plus cos squared theta. The derivative right now is squared. Let's see how that one will look. First of all, let's take the derivative. The derivative of 1 minus cos theta right now is literally just going to be sine theta. And if you square that, then we get sine theta squared. So if I put these components into my integral, I know that I'm integrating from 0 to pi right now. And then I have r squared, which turned out to be this. Don't forget your square root. 1 minus 2 cos theta plus cos squared theta. And then we add the derivative with respect to theta squared, which turned out to be this. All right. And then we integrate that with respect to theta. Now, this cos squared plus sine squared situation vanishes in favor of 1. And so your integral here simply becomes now the integral from 0 to pi of the square root of, let's see, we got 1 here, plus 1, so 2 minus 2 cos theta d theta. And you might look at this and say, there's no way that this is getting simplified. I can't use a u sub right now to save this. I can't even do integration by parts. So what can I do? Fortunately, again, you should be aware of your trig identities. And essentially here, it's a half angle formula that you can use, but we can basically use the double angle formula in reverse. Let me explain. So cos of theta over 2 here, we can think about that, if it's squared, as 1/2 minus 1/2 cos of theta. That's, again, the double angle formula, but for theta over 2 instead of theta. Typically, you'll see it written like this. But it's the same thing. If you change the theta into theta over 2, you must divide both of these thetas by 2, basically. So you get theta over 2 and then theta on the other side. So either you start by the half angle formula if you know it by heart, or you start from the double angle formula and rearrange it. It's the same deal. And you can see here that if I want to isolate right now for this, I bring it on one side. I have 1/2 right now, as you can see, cos of theta. And then we have on the other side 1/2 minus cos squared of theta over 2. And essentially here, what needs to happen is, again, what I'm trying to do is replace this in favor of theta over 2 squared. So I'm hoping, again, to get a cancellation to happen. That's exactly what I'm trying to do. So I need here to multiply now both sides by 2. So I get here cos of theta equals to 1 minus 2 cos squared of theta over 2. And so I take this, right, and I will plug it in to here. That's my next move. So we have remaining now the integral from 0 to pi. Alrighty, from here, the square root 2 minus 2, and then we'll plug in our result from the trig identity. Nicely and conveniently. Right in there. Okay, and from here, I can see clearly that these numbers are going to cancel. We're going to get a 0. And then we are remaining with a positive right now. Positive here, 2 cos squared theta over 2. So let's write it out, what remains, being really careful. 2 cos squared theta over 2. All right. And now from here, we can distribute the square root in the two terms and essentially have root 2, and then when we distribute the square root to the square cosine, we just get cos theta over 2. Same integral bounds from 0 to pi. And from here, it's really easy now to finalize this. So we've got cos theta over 2 being integrated. That must have come from a sine theta over 2 positive sign. But if I differentiate this, the 1/2 would come out, and I don't want that, so I need to multiply this result by 2, in that if I differentiate this now, I'm going to get exactly this guy over there. All right, so we ended up with a 2 root 2 here as a constant, and then sine theta over 2 as the function part. We're still evaluating this from 0 to pi, and if I go ahead and do so, I get 2 root 2, and then sine of pi over 2, which I very well know is going to be 1, and then minus sine of 0, which I very well know also is going to be 0. And then I remain here with 1 times 2 root 2, or just 2 root 2. Very satisfying finish here. So that is this example, a little more cumbersome, but you can see in this kind of situation how important it is for us to know our trig identities well, so that we can abuse them and save ourselves from the situation by introducing a square term and canceling the constant that was bothering us, so that the square root can basically vanish and not bother us anymore while we do the integral. All right, so this is again how to develop the Arclength formula for polars and apply it in a couple of examples. If you found, again, this information helpful, consider subscribing. Other than that, thanks for watching.